Welcome to The Explainer. We're all about breaking down the big topics by going straight to the source. It sounds like a pretty simple question, right? But honestly, this one question is at the heart of a massive cosmic mystery that has scientists scratching their heads. And we're not talking about a tiny little disagreement here. Nope. This is a full-blown crisis that might just be pointing us toward a whole new understanding of physics. Okay, let's dive in and see if we can unravel this thing. Okay, so think of this as a cosmic detective case. And our first job, we got to understand the crime scene. And the crime scene is this. We've got two totally different speeds for the exact same universe. So this whole thing revolves around something called the Hubble constant. You can basically think of it as the universe's speedometer. It's this super important number in what scientists call the cosmic rulebook, the standard model of cosmology. It tells us how fast galaxies are speeding away from us. And here's the kicker. Almost everything we think we know about the cosmos, well, it's all built on the idea that we've got this one number right. All right, so our first set of clues takes us way, way back. To the very beginning of time itself. This is what's called the cosmic microwave background, or CMB. It's basically the faint afterglow of the Big Bang. Think of it like the universe's baby picture, taken when it was just a tiny 400,000 years old. And by studying the little hot and cold spots in this picture, scientists can use that cosmic rulebook we mentioned to fast forward all the way to today and predict how fast the universe should be expanding right now. And when they do that math, using incredibly precise data from the Planck satellite, they get a number. That number is about 67 kilometers per second per megaparsec. Whoa, okay, what does that mean? It just means that for every 3.3 million light years you go out into space, a galaxy should be moving away from us 67 kilometers per second faster. So just lock that number in your head, 67. Okay, so that was clue number one. Now let's look at our second set of clues. And this time, we're not talking about predictions from the past. We're talking about direct, hands-on measurements of the universe as it is right now. So how do you measure the universe? Obviously, you can't just stretch out a giant tape measure. Instead, astronomers have this really clever method called the cosmic distance ladder. It's all about building up our knowledge step by step, or I guess rung by rung, starting with things that are close by and using them to figure out the distance to things that are way, way out in the cosmos. And this is a great way to see how it works. The whole ladder is anchored at the bottom with pure, simple geometry for things nearby. That first rung helps us calibrate the next one, which uses special pulsating stars called Cepheids. Then we use those Cepheids to calibrate the top rung, a certain kind of exploding star, a type Ia supernova. These things are so incredibly bright, they act like standard candles we can see across the entire universe. It's really painstaking work, pioneered by teams like the SHOES project, which is led by Nobel winner Adam Rees. So they go through all that incredible work, they measure everything. And what number do they get? About 73. That's not 67, is it? It looks like the universe today is expanding faster than our model from the early universe predicts. So here's our problem. We've got two of the best, most precise measurements in all of science, and they flat out disagree with each other. This is the heart of the crisis. It's what everyone's calling the Hubble tension. And I really want to stress this point. We're not just looking at two numbers. We're looking at two completely different ways of measuring the universe. One method looks at the ancient past, at the baby universe, and uses our best theories to predict what's happening today. The other method looks out the window right now and measures it directly. And the two answers, they just don't match up. And if you look at the data, the gap between these two values is huge. Their error bars, the little windows of uncertainty, they don't even come close to overlapping. The disagreement has now hit what scientists call a 5 sigma level of certainty. Now, to put that in plain English, that means there's less than a 1 in a million chance that this is all just some random fluke. This is real. And that's why you see quotes like this one from Adam Rees. He basically says, unless a whole bunch of different scientists made unrelated mistakes, it's looking more and more likely that this isn't a bug. It's a feature of the universe. So if it's not a mistake, what on earth could it be? Let's check out the main suspects. Okay, back to our cosmic detective story. When it comes to what's causing all this, there are really two main lines of inquiry. The first suspect is just faulty measurements. Could there be some hidden error, some systematic, as they call it, in one or both of the methods? For years, this is what everyone focused on. Scientists were double, triple, quadruple checking everything. They used different telescopes, different stars, you name it. But here's the thing. As more and more independent checks come in, they keep confirming both results, which means the evidence is starting to point away from measurement error and toward our second suspect. Maybe our cosmic rulebook itself is just incomplete. And this is where it gets really, really exciting. Because this tension might not be a problem at all. It could be a doorway to brand new physics. I mean, look at these ideas. Maybe dark energy, the stuff that's already accelerating the cosmos, isn't constant. What if it's getting stronger over time? Or what about something called dark radiation? That could mean a whole new type of speedy little particle, like a sterile neutrino, was zipping around in the early universe, messing with the expansion rate. Or maybe dark matter isn't so, well, dark and boring. What if it interacts in ways we haven't even dreamed of? The cool thing is, any one of these wild ideas would change the recipe of the early universe. And if you change that recipe, you change the prediction from that baby picture, and poof, the tension could disappear. So you might be asking, why does any of this matter? Well, it matters because a crisis in science isn't a bad thing. In fact, it's often the first step toward a massive revolution in our understanding. And honestly, we have seen this movie before. Back in the 1990s, there was another huge crisis. The universe, according to the calculations, seemed to be younger than its oldest stars. Which, yeah, that's literally impossible. It made no sense. And that paradox, that crisis, forced scientists to a mind-blowing discovery, that the universe's expansion is accelerating. It led them to discover a whole new force of nature, dark energy, a discovery that changed everything and won a Nobel Prize. So, you see, the Hubble tension isn't a failure. It's a clue. It's a giant flashing arrow pointing us towards some new, profound discovery. This isn't the end of the story. It's the absolutely thrilling start of a whole new chapter in our quest to figure this place out. The real question isn't if our cosmic rulebook is going to be rewritten, it's just how big the rewrite's going to be.